I want you to try a visualization exercise with me, just for a second. Close your eyes and picture the most advanced computer in the world, a quantum computer. What do you see?
I think for most of us, it's the same image, right? It's that golden
Like a
chandelier.
steampunk-looking thing.
Yeah, all those gold tubes and twisting wires, and it's always hanging inside some giant frozen vacuum chamber. It looks like a prop from a Marvel movie.
It looks expensive.
Yeah.
And complicated, and frankly, a little terrifying to touch.
Yeah.
But today, we're doing a deep dive on a company called PsiQuantum. And when you look at their quantum computer, well, I have to be honest, it's kind of a letdown.
Isn't that down?
It's boring. It looks like a standard silicon chip. I mean, you could easily mistake it for the thing inside your laptop.
See, I would argue that boring is maybe the highest compliment you can pay an engineer. Boring means it's reproducible. Boring means you can make 1 million of them.
That is a fair point. But here's the kicker, and this is why we're doing this today. This boring-looking chip isn't moving electricity around. It's not using electrons. It's running on light, actual particles of light. They have taken the fastest, most fleeting thing in the entire universe, something that literally never stops moving, and they've somehow trapped it to do math.
It is a complete inversion of the industry standard. I mean, most quantum computing is about trapping matter atoms, ions, and just holding them perfectly still in a vacuum.
Right.
So quantum just said, forget matter. Let's use light.
Which sounds, I don't know, poetic, but it also sounds like an engineering nightmare.
Oh, it is. It's incredibly difficult. But the payoff, if they pull this off, is that they aren't just building a science experiment in a lab. They're building a factory.
So today, we are going to unpack exactly how this works. We're going to get into things like heralding photons, space-to-time conversion, which is a total mind-bender, and these crystals that operate at speeds that just shouldn't be possible.
The goal here for you is to understand why they chose this harder road. I mean, why switch to light at all?
Let's start right there. Why light? Because, you know, usually when we talk about quantum computers, we talk about qubits made of matter, superconducting loops or trapped ions. Why throw all of that out and use photons?
The biggest reason, really, is durability. In the quantum world, the #1 enemy is decoherence.
Which is just a fancy word for forgetting.
Basically, a qubit can be a 0, a 1, or both at the same time. But matter-based qubits are just incredibly fragile. Think of them like an ice cube sitting in a sauna.
Okay.
You have to work so hard to keep that ice cube from melting. You need a vacuum chamber, temperatures near absolute zero, magnetic shielding. But even then, if someone, sneezes in the next room, that vibration might be enough to melt it.
And that's decoherence. The information is lost.
In microseconds, exactly. So matter is fragile. It interacts with everything.
Okay.
Now compare that to a photon. A photon is more like a diamond. It doesn't melt. Photons don't really interact with each other, and they don't interact with the environment unless they hit something head-on.
So they don't decohere.
Barely at all. I mean, think about the cosmic microwave background radiation.
The leftover light from the Big Bang.
Exactly. Those are photons that have been traveling through the chaotic mess of the universe for 14 billion years. And when our telescopes catch them today, they still hold the same polarization state they were born with.
That is wild. 14 billion years of data storage without any corruption.
Versus microseconds for a matter qubit. So if you want to build a system that can scale up, do you want the ice cube or the diamond?
Put it that way. I'll take the diamond. But there's another angle to this too, right? It's not just about the qubit itself. It's how you connect them.
Connectivity is the real bottleneck. A useful quantum computer needs millions of qubits. You just can't fit millions of qubits on one single chip. You have to connect chip A to chip B to chip C.
Like a data center. You have racks and racks of servers all talking to each other.
Precisely. But how do you get a trapped ion and atom stuck in a vacuum chamber to talk to another atom in a different chamber down the hall?
Atoms don't move. You can't send an atom through a wire.
So matter-based computers are kind of stuck in their box. But photons are the internet. We already have a global infrastructure fiber optics designed specifically to move photons from one place to another.
So PsiQuantum is betting that by using light, they get all the networking for free.
Well, free is a strong word, but they're definitely playing on home turf. They're using the only medium we know of that can connect modules together at scale.
Okay, the logic holds up. Light is durable, it connects easily, but now we have to talk about the hard part. Because you can't just flip a light switch and have a quantum computer. You need very, very specific light.
You need a clock.
In a normal computer, a clock is just a quartz crystal ticking, right? Tick-tock, move the data.
Right. In this photonic system, a photon is the clock. But not just any beam of light. You need exactly one photon.
Why just one? Why not just use a laser beam with, like, a trillion photons?
Because quantum mechanics is all about probability. If you're running a calculation based on the interaction of particles, having two photons show up just creates noise. It ruins the math. Having zero photons while the computer stops. You need a single, solitary photon on demand every single time.
How do you even manufacture one single photon? I'm assuming you can't just use tweezers.
No tweezers. They use a structure etched into the silicon wafer called a ring resonator. Just imagine a tiny circular racetrack. They fire a green laser into this track.
So this green light is just spinning around this ring.
Thousands of times. It builds up intensity. And because silicon has this very specific property, it's a third-order nonlinear optical response, something like magic happens.
Magic or physics?
Sufficiently advanced physics. It's called four-wave mixing. And occasionally, two of those green photons in the pump laser will collide.
Like a tiny car crash.
Sort of. And out of that collision, they vanish, and two new photons are born, but they aren't green anymore. One is high energy, so blue, and one is low energy, red.
Why do they change color? Why not just stay green?
Conservation of energy. You can't get something for nothing. If one photon jumps up in energy to become blue, its partner has to drop down energy to become red. The total energy stays the same.
So they're born as twins, a red one and a blue one.
Always twins. And this is crucial. This is how they solve the whole tree falls in the forest problem.
Which is, if you measure a quantum particle, you destroy it.
Exactly. You have to know the blue photon is there to use it for computing. But if you look at it to check, you absorb it. It's gone. You can't use it.
It's the ultimate catch-22. I need to know you're there, but if I check, I kill you.
So PsiQuantum uses the red twin. They call it the heralding photon.
Yeah.
Think of a herald blowing a trumpet to announce the king is coming.
Okay.
They filter out that red photon and send it straight to a detector. If the detector goes click, they know with 100% certainty that the blue twin was created at the exact same moment.
Okay, but hold on. If you destroy the red photon to check for it, aren't you just sort of guessing that the blue one is still there? What if the blue one got lost?
Well, that's where the smart engineering comes in. The path for that blue photon is incredibly short and efficient. Because they were born from the same event, that collision in the ring, their existences are correlated. If you see the red, the blue is there. You don't have to look at the blue one. You just have to trust the red one's sacrifice.
So you sacrifice the red one to confirm the blue one exists, and then you switch the blue one onto the main computer track.
Yes. They call that the world line.
But this creates another problem, doesn't it? You said switching. We're talking about light. Light travels at, well, the speed of light.
About a foot per nanosecond?
So in the time it takes for that red photon to hit the detector and send the signal, I'm here, the blue photon is already moving. It's zooming down the wire. You have to open the gate before it just crashes into the wall.
And you have nanoseconds to do it.
How do you switch something that fast? I know standard silicon heaters take microseconds. That's 1,000 times too slow. The photon would be a mile away by then.
This was one of their biggest hurdles. They had to introduce a material that silicon manufacturers absolutely hate. It's called barium titanate oxide, BTO.
BTO sounds like a classic rock band.
It acts more like a villain in the manufacturing process. It's a crystal, a ferroelectric material, but it has a superpower called the Pockels effect.
Which does what?
When you apply a voltage to BTO, its atomic structure literally shifts instantly. And that shift changes its refractive index. Basically, it changes how fast light moves through it.
So by changing the speed of light in just that tiny section, you can steer the beam.
Exactly. It's like a railroad switch. But instead of moving the track, you're changing the density of the air around the train to make it turn. And BTO can do this at gigahertz speeds.
Fast enough to catch the blue photon.
Just barely.
Yeah.
But there is a catch. You can't just glue BTO onto a silicon chip.
What?
Silicon is incredibly orderly if atoms are lined up in a perfect grid. BTO is, well, it's complicated. Its crystal structure doesn't match silicon's. If you try to grow BTO on top of silicon, it's like trying to stack Lego bricks on top of Duplo blocks. They just don't fit.
The crystal would just crack.
It cracks, it creates defects, it ruins the whole chip. This is what they call the dark art of their process. They spent a decade figuring out how to lay down a buffer layer atom by atom to transition from the silicon lattice to an oxide lattice, and then finally to the BTO lattice.
So they basically built a molecular staircase just so this switch could sit on the chip.
Correct. And without that one specific manufacturing breakthrough, the whole computer doesn't work. You can't route the photons fast enough.
It's amazing. The future of computing relied on figuring out how to layer two different kinds of rock on top of each other without them cracking.
Material science is usually the unsung hero in all of this.
Okay, so we've made the photon, we've heralded it, we've routed it with our BTO switch. Now we have to actually connect these chips together. And this is where I think the story gets truly sci-fi.
The connectivity problem.
You mentioned earlier we use fiber optics because it's the standard. But isn't there a big problem with sending quantum data through a regular fiber?
A huge problem. It comes down to how PsiQuantum encodes information. They use something called spatial encoding. So imagine two parallel paths on a chip, path A and path B.
Got it.
If the photon is in path A, it's a 0. If it's in path B, it's a 1. If it's in both, that's your superposition.
Disciplina?
But if you want to send that qubit to another chip through a fiber optic cable, you have to send both paths. And here is where physics just bites you. Fiber optic cables are not perfect. They vibrate, they expand and contract with heat.
We're talking microscopic changes though, right?
It doesn't matter. If someone walks down the hallway near the cable, the fiber might vibrate by just a fraction of a wavelength. That tiny movement changes the length of the path. And in quantum mechanics, the phase of the photon depends on the path length.
So if the path length changes, the data changes.
It's instantly corrupted. It's called phase drift. You simply cannot send a spatial qubit through a long fiber. It's far too fragile.
So what do? Do they have to shield the fiber somehow?
No, that's impossible to do perfectly. Instead, they do something called space-to-time conversion.
Space-to-time conversion. That sounds like something out of Interstellar.
It's brilliant. Remember how we said light travels about 1 foot per nanosecond?
Right.
So distance is time. Before the photon leaves the chip, they take the part of the qubit that's on path B and they force it to take a little detour. They send it through a long spiral of waveguide, literally a coil of wire, that is exactly long enough to delay it by 1 nanosecond.
So they deliberately make the one part of the qubit arrive late.
Yes. So now, the qubit isn't top path versus bottom path. It is early arrival versus late arrival.
They've turned space into time.
Precisely. Now, they take both parts, the early pulse and the late pulse, and they send them down the same fiber optic strand. They're running single file.
Oh, okay. I think I'm getting this.
Think about two runners.
Okay.
If they're running side by side holding hands, that's spatial encoding. If the road is bumpy, one runner might stumble or the road might slant and they lose their grip. The connection breaks.
Right.
Now imagine they're running single file, one behind the other. If the road bumps...
They both bump.
Exactly. If the fiber stretches because of heat, it stretches for both the early photon and the late photon. They're both affected equally. So the relative difference between them, that 1 nanosecond gap, stays perfectly preserved.
That is just genius. They're using the noise against itself.
It effectively cancels out all the environmental noise.
And does this actually work? I mean, in the real world? Or is this just a whiteboard theory?
They proved it. They did what they call a tunneling experiment. They ran a fiber optic cable 250 meters under their lab, literally through the building's infrastructure.
So next to the HVAC and the elevators and all that?
Everything. All the vibrations, temperature swings. And they sent these time-encoded qubits through it. They maintained 99.7% fidelity.
Wow. 99.7% through a standard cable.
It means they can take a quantum chip, plug it into a wall with a standard fiber cable, and connect it to another chip in the next room, and it just works.
That changes the whole picture. It means the computer doesn't have to be one giant monolith. It can be a distributed network.
Exactly.
Which brings us to the final piece of the puzzle, the vision. We talked about the chandelier versus the chip, but where do these chips actually live?
They live in what PsiQuantum calls MK2 cryostats. But don't let the name fool you. These aren't little lab tubes. They are 4-meter-tall steel cabinets.
They look just like server racks.
They are server racks,
Yeah, okay.
just very, very cold ones. PsiQuantum operates their chips at 2 Kelvin.
Which is about minus 271 Celsius. I mean, that is still incredibly cold.
Yeah, it's deep space cold. But, and this is the key, in the quantum world, 2 Kelvin is practically tropical.
How so?
The chandelier computers, those superconducting qubits, they operate at 20 millikelvin. That is 100 times colder than PsiQuantum's system.
Does that difference really matter that much? I mean, once you're that cold, you need specialized equipment regardless.
It matters immensely. Think of it in terms of your cooling budget. At 20 millikelvin, your budget for handling heat is a whisper. A few microwatts of heat and the whole system crashes.
So it's extremely fragile.
But at 2 Kelvin, your cooling budget is a shout. You have thousands of times more cooling power. You can handle the heat from all the control electronics. You can pump liquid helium through the racks, just like you'd use water cooling in a gaming PC.
So it stops being a physics at the edge of reality problem and becomes a plumbing problem.
Exactly. And
Yeah.
that is what allows you to build big. They are already constructing sites in Chicago and Australia that are designed to house hundreds of these cabinets.
And that's the shift, isn't it? They aren't trying to build one super powerful brain. They're trying to build a warehouse full of modules that can all act as one brain.
That is the vision.
Yeah.
Utility-scale computing.
So let's just try to summarize this Rube Goldberg machine because there are a lot of moving parts here.
Sure.
Step 1, we use a ring resonator to spin green light until it spits out twin photons, a red one and a blue one.
Conservation of energy at work.
Step 2, we kill the red one to herald the blue one. Then step 3, we use that BTO crystal, the one that hates silicon, to switch the blue photon onto the main track at gigahertz speeds.
Right.
Step 4, we convert the data from space into time by delaying the signal so it can survive a long trip through a normal fiber optic cable.
And finally, step 5. It arrives at another chip, gets converted back, and hits a nanowire detector that's kept at 2 Kelvin.
And the detector heats up, the superconductivity breaks, we get a little voltage spike, and that's our answer.
Simple, right?
It sounds impossibly complex. But the crazy part is, every single step we just described is based on manufacturing processes that we already understand.
That's the so what here.
Yeah.
So quantum is betting that the best way to solve quantum computing isn't to invent some brand new physics. It's to force the physics to fit into the tools we already have. Silicon manufacturing, telecom fiber, cryogenic pumps.
It stops being a Nobel Prize problem and starts being a supply chain problem.
And historically, humans are really, really good at solving supply chain problems.
So I want to leave you with a final thought today. We tend to think of the ultimate computer as a monolith. HAL 9000, one giant machine in a room that knows everything.
Right. The oracle.
But if PsiQuantum has really solved this connectivity problem, if they can just link cabinet after cabinet with fiber optics, treating distance as time, does that mean the future of quantum computing isn't a single machine at all?
It's a web.
It's a distributed internet of quantum modules. And if that's true, what happens when you just keep plugging in more cabinets? Is there an upper limit?
Or do we just keep adding racks until we can simulate the entire universe?
That is a terrifying and exciting question to end on.
Indeed.
That's the deep dive for today. Thanks for visualizing the invisible with us. We'll see you next time.